Welcome back to the Home Lab, and I've got a really interesting device and build to share with you today. What we're going to look at is the really unusual ins and outs of the Tesla valve. Just before we start, I want to say a huge thank you to my sponsors PCBWay, who always encourage me to make more videos. And if there was ever a video that would benefit from their work with 3D printing or CNC machining, it would have been this one, because I cut this out myself and it wasn't an easy project. And if you're thinking of making a Tesla valve, you'd probably want to make one that's much longer than this and perhaps a little bit smaller. Anyway, go and have a look at their website. There's a tab on the website that says shared projects, and there's some really good ideas there for projects that you might want to try as well. As you might guess, the Tesla valve was invented by Nikola Tesla, the Serbian-born American electrical engineer. An absolute genius who was said to have a photographic memory, and he was famous for his work on electrical engineering. I'm sure you've all heard of the Tesla coil and many of the inventions that he did with AC, alternating current, we use to this day. He was said to be inspired by his physics teacher, which makes me feel good. I wasn't his physics teacher, of course, but it means that quality teaching is important to inspire future generations, so we all try our very best. Anyway, he died in relative obscurity in 1943, and yet he had over 300 patents to his name, and many of his inventions we still use now. Now, if you're a physicist like me, of course, you'll know the Tesla as the unit of magnetic flux density, sort of how strong a magnetic field is, with the Earth's being very weak, less than 1, and superconducting magnets being in the order of 1, 2, 3, 4, 5 Tesla. It's interesting how that unit came about, because it came about well after Tesla had died at the Paris Conference of Weights and Measures in 1960. And a chap called Franz Avcin suggested that we should remember Tesla, sort of rather unknown at that time, by naming a unit after him. And it's really appropriate unit because it's about magnetism. Just before we finish on this bit, Franz Avcin is a really interesting character and scientist as well, a really intriguing man. And after this video, I really recommend you Google him and see all the wonderful, interesting hobbies and things that he got up to. So we're going to look at US patent 1,329,559, which is Tesla's patent for a valvular conduit, a kind of one-way device for fluids. It's a sort of form of diode or check valve. So what I'm going to do is show you how it's constructed, and then we'll demonstrate it working, and we'll show how it does very effectively, with no moving parts, reduce the flow in the opposite direction. As I said, Tesla's valvular conduit is a kind of check valve, and check valves are used in fluid flow situations where you want to restrict the flow in one direction. You want to have sort of diode properties. In other words, you want to have the flow going one way but not another way. And there are lots of ways to do that, but if you think about it, most of the ones that are used, in fact all of the ones that are used apart from this, use moving parts. Typically the heart is a very typical use of check valves, where you've got bicusp and tricusp valves that open up and then when the flow reverses, close. I often think of lock gates on a canal that are actually forced closed by the water pressure. But the thing is, all of these situations have moving parts, and they're not going to be particularly good in situations where the material is highly corrosive, or you're going to need bearings, or you're going to need parts moving through from the outside of the pipe where you might get leaks, etc. Or you have to service them frequently, or particularly, and Tesla thought about this, where you want a check valve when the flow is pulsing very rapidly, so going forwards and then not backwards, and then forwards and then not backwards. So Tesla had a reason for inventing this, and we'll talk a little bit more about that later. But it's a very, very clever design that will not completely block, but reduce the flow in the back direction and will allow free flow in the forward direction. So it acts a little bit like a diode. It's a form of check valve with no moving parts. So to demonstrate this to you, I had to build my own little Tesla valve, and I went back to his original patent and made a drawing from his original drawing. Now, his had actually 11 of these little segments in the valve. I've chosen only to do 3. In fact, if you look very carefully at his original patent and mine, I would call it only not 11, but I would call it 10 and a half, because this final one is not quite the same shape as these. It doesn't have such an effect on the flow. So I'd like to think of mine as a sort of 2.5 segment Tesla valve, where his was a sort of 10.5 one. So I made it out of sheets of Perspex, my usual way of buying A4 Perspex, and out into the garden, and the bandsaw cutting away and breaking bandsaw blades and all that sort of business, with one yellow sheet behind, and then I cut out from a big thick sheet of white Perspex, and I had to keep reminding myself what I didn't want. Normally you cut out the shape and it's the shape you want, but in this case it was actually the inside part that I didn't want, and I needed to keep the offcuts, as it were, and I had to think really carefully that I didn't make a mistake and damage these parts. And then finally a clear sheet on top. Now, it was interesting that my feeling was this is used for liquids or fluids, and I didn't really want to glue this together and make it liquid tight, so I thought, I'll tell you what I'll do something different, and I don't think it's been done before on YouTube. I'll make my Tesla valve and I'll demonstrate it to you with particulate material. So we're going to use some very small ball bearings and pour those through it and see just how it works. Right, let's demonstrate this working. Now, I've moved the camera a long way back just to show you the apparatus. So I've got a funnel here and the Tesla valve and something to collect 8,000 little steel 3mm ball bearings. And what we'll do is we'll then demonstrate it a second time, and we'll zoom in and you'll see it working. So this is considered to be the sort of forward direction of the Tesla valve. So let's pour them all in and see how we get on. Right, we're zoomed in now. So what I'm going to do is I'm actually going to time how long it takes for the little 3mm ball bearings to go through. And remember that this is the forwards direction, and then we can do it in the reverse direction and compare the flow rates and work out the diodicity of this device. So 3, 2, 1, go. So I've turned it upside down now, and we've got the direction that should restrict the flow. So let's pour in the little ball bearings and see how long they take to go through. 3, 2, 1, go. So the flow through it there was definitely slower, but I think as a working Tesla valve, it's not the very best example, because the little ball bearings here have actually stuck in these little side roots. And I think if I made them a little bit lighter and maybe use plastic beads or something, then we would get more flow here that would come upwards and restrict the flow coming down even more. Well, I'll leave it for you to judge whether that's been an effective test or not, and maybe I should repeat it at some stage with some different particles, or maybe seal this up and try it with a liquid. But as you can see, if these ball bearings were moving downwards and then moving up, they would restrict the flow coming through. All of that said, it's good fun and it's an experiment, and what we'll do now is we'll look at the ratio of the times and see whether we can calculate a diodicity for this valve. Let's now try and work out the diodicity of our Tesla valve. Now, you might remember when you were younger doing water circuits. These were pipes of water that simulated how electrical circuits worked. And you can imagine diodicity in Tesla valves in the same way as a water circuit. In other words, a Tesla valve acts rather like a restriction in the flow, in other words, a resistor in an electrical circuit. And a resistor has a pressure difference to drive the current through it from one side to the other, the potential difference, what we call the voltage across it. And the same is true of the Tesla valve. If you want a constant flow through it in either direction, you can apply a pressure across it, and there's a bigger pressure drop if the valve is not passing fluid through very easily. In other words, it's in the reverse direction. Now, I didn't use a constant flow rate through mine. I just poured the ball bearings in. So we're going to do the FJ diodicity. And the way I'm going to do that is I'm going to divide the time that it took for the ball bearings to go through in the forward direction and divide it by the time it took for the ball bearings to go through in the reverse direction. So I get 7.06 divided by 5.96, and that gives an FJ diodicity of 1.2. In other words, it's restricting the flow by about 20% in the reverse direction. Now, I only had 2 of those little bucket valves in mine, or maybe you could say 2.5, but really only 2 that were functional. Tesla suggested you can get up to diodicities in fluids of numbers up to about 200, which is truly incredible. Now you've seen it working, it might be a good time to discuss why did Tesla ever come up with this idea. And what you've got to remember with Tesla was he had this amazing brain for inventing things, but he didn't really invent things in isolation. He invented something that was solving another problem. And he was really interested in electricity generation. He invented the Tesla turbine, which should be the subject of another video. But what he wanted to do was he wanted to drive the Tesla turbine with a pulse jet engine, and a pulse jet engine sort of produces sort of pulses of power very rapidly, and the fuel goes into the combustion chamber, and then you have to block off where the fuel comes in. So there are check valves to stop the exhaust flow going backwards, and this happens very rapidly, and they can wear out very quickly. So Tesla thought, I wonder if I can make the valves into my pulse jet feeding the fuel into the combustion chamber have no working parts, and that's where he came up with the Tesla valve. And I believe there's some drawings that you can see of Tesla valves in a pulse jet engine. I'm not sure he ever really completed that project, but it's a really interesting use. Do they have any use to this day? Well, yes, they do, in microfluidics. I can't even say that, microfluidics. So this is where you're sending really, really tiny amounts of fluid into a system. It's something you'll have to Google and look up. And the Tesla valve is used to stop flow going backwards, or at least to massively reduce that. And I think as time goes on, and perhaps if we go back to pulse jet engines, we will see more and more Tesla valves being used. So I do hope you enjoyed that video on the Tesla valve. It's a really interesting device, isn't it? Now, if you're into building things, why don't you have a go at making one? You can 3D print them or CNC machine them. And if you're using equipment like that, you can probably make one with more of these areas in it, more than I made. Remember, Tesla's had 11 originally. And give it a go. And perhaps if you do a 3D one, you can give it a go with some liquids. Anyway, I'll be making another video soon. And as ever, I look forward to seeing you then.